So now let's continue. Let's see, guys, let me put myself here, and I'm just arranging the screen. Now we are continuing to study, or we've been studying, remember, the 3 components in all machine learning algorithms. And I hope this is really helping you, this framework, because then it's really easy to understand everything. So all ML algorithms, 3 components. So today we will study the optimization, but first let's remember the hypothesis class for the neural networks. Hypothesis class. So for neural networks, second, okay, maybe let's just say 2, we define a loss or objective function. So we define this, and then we do our optimization, optimize, right? Or let's say optimization. So today we will also study this. Now for neural networks, we continue this and then the optimization today. Remember last time we actually studied different loss functions. It was measuring how good a hypothesis function is. This hypothesis class is doing the mapping. Actually there is X, maybe data distribution, like Fariba was asking, and training samples. This is mapping this. For instance, this is a neural network hypothesis class. This is actually what I mean. I mean, somehow we also map it to some prediction, and from there, remember, we define a loss function with the ground truth, meaning how good I was able to predict something and what was the real expected true value there, right? And then optimize, meaning these guys had some parameters, and from the theta, of course, also the third step. And this is the loop, actually. You see, it looks simple enough, but of course, all these components can be changed, and then you have a different ML algorithm. Okay, so let's continue with this nonlinear hypothesis class, neural networks, guys. Neural networks. We said these neural networks currently we are working on are also called fully connected or artificial neural networks, ANNs. Sometimes we call them MLPs for historical reasons, multi-layered perceptron. Remember, we looked at the history in the first class, first lecture, overview lecture. Sometimes that's why we call it MLPs, because perceptron was one of the first neural networks that was inspired from, again, the brain's neuron computations. Okay. So let's maybe do a simple example here with this hypothesis class. Example, for instance, I will do a multi-class classification model. I will just design one here, and because I know how to work with the components, it's easy for me. I can say it's gonna be a n layer neural network, ANN, let's say. This is then setting my hypothesis, right? So for instance, let's do this. Let's say I have an input. Sometimes I also show my input as the zeroth activation, or let's just show it as X. These can be shown as vectors at this point. And these are, of course, coming from, like I said, my data generating function or distribution I1 to M. M is, remember, the data or sample complexity. I think we skipped that, this classical ML capacity, sample complexity, this Watnick dimension. Maybe after we do today's optimization, if there is time today or next time, I can just summarize it quickly. But today we have to work on backpropagation because that is in your homework. By the way, your first homework is assigned already, and it requires to code, of course, backprop from scratch, as I think every such homework involves. So also for a supervised classification problem, I'm also given the corresponding labels, right? So these are labels. Now let's just put the backbone, the network here. So A0, of course, I'm trying to produce a first activation, right? I mean, these are, sometimes we show these like, okay, there are some arguments of the activation here, and this is coming through, of course, going through the model. I will write the math, but weight parameters and bias parameters. Okay, let me first put the backbone, and then we can actually talk about the model parameters in between. I produce all these activations. Of course, there are also these guys, right? The result of the affine layer, then nonlinearity, I have the activation. Okay, so this is, I said n layers, so I should just do a dot, dot, dot. The same pattern is repeating, and that's the idea of these deep networks, right? We take the same type of blocks and we repeat it for many, many layers, and this is the depth. This direction is the depth of the network. So let's say this is my an minus 1. Okay, so guys, this is superscript. I'm using superscript, you see, superscript to show the index of the layer. So n minus 1 activation, and remember, typically I mean, this could have been my an, but zn. Okay, let's also show an. Typically, actually, this is, instead of this zn goes out as my hypothesis, we call these logits, remember? Or let's maybe not give a notation. It's the linear affine layer output, and h theta x, this is the hypothesis, okay? The first component. So it's, let's say, my zn, the output of the affine component of the last layer. This is my hypothesis function. So this is defined. Once I put down such a network, hypothesis function. So I should also put down my parameters. For instance, omega, the second layer, omega 2, B2, right? Omega 3, B3, etc. So omega n minus 1, Bn minus 1, omega n Bn. I mean, these double underscore are matrices, remember? So we are done by defining our hypothesis function, and this is a vector, by the way, right? Like a vector function currently. Takes this all the way from, this is a vector 2. Now define, for instance, I said it's a multi-class classification. I have to define the second one. For instance, let's say I want to use my hinge loss, multi-class hinge loss. Okay, just say, let's write this guy, my LSVM, so that is loss SVM, right, of theta. Theta r, remember all these, theta are all these guys, omega 1, B1, you know, we've been talking about this theta, right, the parameter vector matrix. Typically we make it a vector, actually. We vectorize it, although I have matrices, you see. We'll deal with it. Omega 2, B2, omega, and the last layer, Bn. These are the parameters. And typically, I should also note, typically the last layer is used without the activation. The last layer is used without activation function. To be able to use the full vector there without squashing it. That's why. That's the idea. So remember now the hinge loss, the second component is we try to say, hey, I need to really have something that compares my activation for each of the input data, each instance of the input data, right? H theta xi and yi. And here for the LSVM or the loss SVM, I have, let's say, actually, I would need to sum this up for all M, LSVM. Now, this is, let's write this, remember the hinge loss. So this is for all data instances. I need to do this hinge function here. Okay, max, remember 0. This was the idea, H theta xi j. So this is the score j in a way, right? Sj. This is the jth argument of the vector function h, okay? Jth arguments of vector function h, actually, I mean, this is vector, minus h theta xi, and then for the true class, because I know it during training, of course, plus 1. This is the hinge, right? Hinge loss. I have a margin. The distance between the scores of other classes to the true class, actually, plus 1. I mean, they should be at least plus 1 more than, no, the true class should be at least, it should have a score of at least 1 plus, right, than the other classes scores. That's the idea. So training, now we will come to the third component, guys. We've done the loss, the hypothesis. The third one, optimization or training, right? Optimization or training. Actually, this optimization, in this case, training the neural network, is really equivalent to estimating theta, the parameters theta. This is what we will be doing, right? So we define now, for instance, I already defined a multi-class classification model for you with an SVM or hinge loss, which uses a multi-class hinge loss, multi-class. You can easily go ahead and, for instance, play with the parameters of this guy. So now, today, I said we will mainly work on this part today. So how do we optimize? How do we optimize the loss? Okay. This is our question for today. So we are trying to do theta star is argmin. This is the optimum parameter. Argmin theta, right? I mean, these are vectors, of course, but remember, this is our problem. Generally, h theta xi, yi, a loss. First of all, from your optimization class, remember, when do I really nicely optimize this? First of all, I ask myself, is this loss function convex? And I'm asking you, for instance, this one. Let's just assume as this as an exemplar. Is this a convex loss function? I mean, not convex. Look at the form of the hypothesis function. Actually, maybe we could write the hypothesis. H theta is like, remember, H theta x is really like, just do the math here, right? Each of these guys are like this. So I can just start somewhere here. Takes the first one, A0 or X, right? Plus, for instance, for one of the instances, plus B1. So goes through an activation, let's say for the first one. Now goes through again, sorry, superscript. Another layer, right? Another activation. These are nonlinear. That's the thing. That was, remember, the nonlinearity that gives us, that increases our expressiveness in the hypothesis function. F2 plus, I mean, you guys, I think, got the point. You just continue in this way. Maybe I should just do this, and in the end, look at here, omega n probably dot plus bn. Maybe I should have used also here the superscripts. Just okay, right? So this is a highly nonlinear and non-convex looking function plus this guy, hinge loss. We looked at it last time. Even if itself, guys, was some of those functions were convex actually, remember? But then the loss function stayed convex because before we had the simple hypothesis, linear hypothesis, right? I mean, so some of those loss functions were convex, and this was a linear hypothesis class, so we had convex functions, for instance, logistic regression and things like that. But now this is already highly nonlinear and non-convex. Nonlinear doesn't mean, of course, convex or not, but this is making a plus inserted into your loss. It's not convex. So my loss is not convex in this case. And in deep learning, the models we work with are typically, so we work with actually non-convex loss functions. So we work with actually a non-convex optimization problem. Okay, this is our problem. Remember, why do we like convex functions? Actually, with convex functions in a high dimensional space, theta, you see I've already here stacked my theta into, you know, these many parameters. You guys know actually currently, I mean, there are all these deep models with maybe billion parameters, billion. So this is a very high dimensional space, millions, hundreds of millions or billions of them. Very high dimensional, right? In millions or this in billions. Okay. So, but now if it were convex, nicely, remember, we would really like things to be like a ball in maybe higher dimensions. I can try to visualize things like this. Why? Because when things are ball or convex, like when I try to start at some initial estimate, I'm trying to go to some minima, right? And for a convex loss function, all local minima are equivalent to the global minima. That's a nice property to have. Now, remember from your optimization class, there is a search direction I'm trying to go after, right? I need to, wherever I start, I need to look for a search direction. So P is my search direction. How to choose is, it is some, of course, open actually, some active research problem, although we use some typical search directions. L theta, the overall loss, okay, overall loss function. How do I search? So search means this is L of theta, right? I want to take some step, and then at that point, I'm really like at some other loss value. So here I was at a specific loss value. And remember, I mean, we are trying to minimize, of course, the loss. Here, this is what we're trying to do. We are trying to minimize this. This is my L theta, okay? So then actually, hopefully, you know, L theta to L theta plus P, the goal is this decreases, right? We want a decrease in the value of the loss function. So I can, for instance, try to do a gradient, or no, first let's do a Taylor series expansion. Taylor series expansion. First, let's see where things come from actually. Don't memorize it. So this is, I can say, hey, let me write this as, okay, itself, L theta plus a P times gradient theta L theta, right? And the higher order term is 1/2. Remember the quadratic term with the Hessian of the loss function P and there are these are actually higher order terms. We can maybe, I mean, in some of the optimizers we neglect these. And you see here, important thing is how to choose this guy. We say guys, let the search direction, I think you guys have a guess, be in the negative of the gradient of the loss function. Now insert it into my Taylor series expansion, plus alpha square, right? And okay, no, first let's just say, not insert here, just say I was searching or looking at this direction, actually, that's what I wanted to do. Now insert it here, L theta plus, or actually I need to say minus alpha, right? Gradient theta L theta squared. So norm, I need a norm here, norm square L theta. Right, because it's really this guy dot producted with itself, and I know this is positive or non-negative at least, so which is nice. You see, now I have actually, this will become less equal to, right, some positive or non-negative number. Okay, we say, hey, this is a search direction that is worth pursuing, right? And of course, we know this is gradient descent, but you know, this is where it's coming from. And you can also recall, I can ask you recall Newton method, for instance. There, the search method, the search direction comes or looks at proportional to the Hessian. Hessian of the loss function. Okay. This is just a recall. Okay, so gradient descent algorithm. So we are in the optimization part. This is still the easy and nice part. Gradient descent algorithm. Okay. And one nice thing is we can use it, okay, whether loss function, our loss function is convex or not. It is a cool, nice iterative optimization. We can use it whether L theta is convex or not. Okay. So GD, we typically show it by acronym GD, right? GD is theta 0, we have to, it's an iterative algorithm. Remember, these are initial parameters. We have to pick them. This is another thing on its own, how to initialize these millions of parameters. And then we iterate. This is the algorithm, right? Algorithm, iterate until convergence. This is also another design criteria. So these are all design stuff that you have to deal with until convergence, when to stop. But the general form of the gradient descent, we know theta k minus, I mean theta next iteration, theta is theta k, the previous or current iteration minus some step size parameter times the gradient theta L theta, right? So we call this in deep learning rates, of course, this guy, learning rates, maybe you know it in that way, but it's really the step size, and it's one of the hyperparameters, right? One of the important hyperparameters, actually, of these models in deep learning. For instance, I was saying Newton method, e.g., Newton method uses, if I was using Newton method to do this update or iterative update, uses this other search direction, because I used here the gradient search direction, other search direction. So I would have theta updated, I mean theta k plus 1, but okay. Remember, it used actually inverse of the loss, the Hessian of the loss, times the gradient theta, L theta. This is the search actually. So this is search direction. This is my minus with minus, it is the search direction. Do you see a reason why actually we're not seeing much of the Newton iterations? I mean, because I said, hey, here is the gradient descent algorithm, and probably most of you are familiar with it. But I said, hey, here is another way to do this iteration, and it is picking another search direction. But you would be like, hey, why didn't I see Newton methods or this update much before, or maybe never before in this field? Even not before, even the inverse, it is just imagine computing the Hessian, even that, like, right, millions of parameters. It's a, for example, if it's 500 million, then 500 by 500 million, right? Compute that. That's something that you have to invert. But actually, you have some approximate inversion formula. We approximate the Hessian through some first order gradients. But here our note is, like you guys guessed, deep neural networks, right? Millions to billions, millions or billions of parameters. Parameters of parameters, right? So theta is, let's say, 100 million by 1. I say imagine computing this. I mean, this is the Hessian, and also inverting. Imagine computing this plus inverting this. This is really a problem. But there exists some quasi-Newton methods. Probably you heard of these. If your maybe size of your problem is manageable, we approximate in these methods. We approximate the Hessian through gradients. Like difference of two gradients actually. So one of them, please check, is BFGS, for instance. Okay, for instance, EG. This is one of them. Yes, because Newton's methods, you see, has this Hessian inverse part. It really gives us an optimal way of also, you see, setting the step size. Like in the gradient descent, there is that hyperparameter we have to play with. In Newton's method, actually, it gives us the overall thing. There is no parameters to set. Exactly. Your size is manageable. It would work well, and it would also work with both convex and non-convex. But like you guys said, in deep neural networks, computationally, it's not feasible. And Mert is asking if we had the computational power. Yeah, sure. I would say go ahead and use that and try to see if you are overcoming those problems by setting the learning rates. You have at least one less hyperparameter. Good point. Actually, for instance, if this quantum computing arrives, I think there will be many new developments, new improvements, enhancements in this field. By now, also opening up new possibilities in the optimization side, because we will have the computation power to work with Newton method or these other optimizers. That would be probably one of the things to pursue. But currently, we are in these first order gradient descent type methods. We have, I'm going to show its variants, but it's mainly variants of this algorithm currently. Yes, good point. Also, my question from optimization to you is this. You have, let's say, your loss function L theta. I'm going to ask you, because we were talking about, maybe not yet, but is it enough to set? Okay, is it enough to set gradient of the loss function to 0 to obtain your minimizer, to obtain your, I mean, this is from calculus, remember, we minimize by setting it to 0, right? We can also derive this gradient descent in that way, but my question is now separate from that. Is it now set to obtain your minimizer of the loss function? Okay. I'm asking you this. Any answers? My question is, okay, that's another answer, but I mean, another aspect, actually. I'm asking, is that really a local minimizer all the time? Is this a necessary condition? That's what I'm asking. Or is this a sufficient condition, necessary and sufficient? You are told, we are talking about, when I say this, a stationary point, okay? It doesn't have to be a local minimizer. So the theorem, remember, from optimization, necessary first condition, okay, or first order condition, is necessary first order condition for a minimizer if theta star is a local minimizer. You see, this is a necessary condition, local minimizer, and L is, the loss function is continuously differentiable. Then, this is if, and then this is true. I know, you see, this is really like this. I already say that any local minimizer, local, global, doesn't matter. You see, any local minimizer, you give me that thing, theta star. I know it's a minimum. Now I know this. This is the necessary condition, guys. This is 0. This is a necessary condition, meaning actually this is going in this direction. Start with knowing that, assuming that theta star is a minimum, then I know its gradient should vanish at that point, okay? Theta star. But what about, given this, I asked you this, that was the trick. Maybe let's make it another theta. So this is, remember when I say sufficient condition, now I'm going the other way around. Given, I said, a theta star, okay, let's say a theta star, it makes my gradient vanish. Okay, this is true. So theta star in this case is a stationary point. Okay, so for a stationary point, I know the gradient vanishes, but for this is a convex side, and then there is a concave side here. I mean, I'm trying to make this look like something. I don't know if it's, this is, this is, you see, stationary point, it's a saddle point, right? You see the point now, right? A saddle point. I mean, you set this to 0, it doesn't have to be, it's not necessarily a minimizer, could be a saddle point. Saddle point, that's I mean, generally it's called a stationary point. So a saddle point is also, of course, a saddle point is a stationary point. Of course, the minimum or maximum are also stationary points. What do we do for that? For a saddle point, remember, you see this convexity and concavity. If we look at or approach that on the loss surface from different directions, because the Hessian is not positive definite, is not positive definite, right? Because it has a negative eigenvalue, right? It has some negative and positive eigenvalues. So its eigenvalues is not positive definite, not. Its eigenvalues, let's say, are both positive and negative, both, right? It's obvious from the picture. So we need a second order necessary condition theorem, second order. This was first order condition, second order necessary condition. Now let's see what this is. This will say we are adding this. The Hessian exists at this Hessian. So this is the Hessian. Exists. Then we have this and the Hessian positive definite. Oh, okay. L. Okay, now I will write the whole theorem actually. I need now the sufficient condition. This is this way. For any local minimizer, you see necessary condition. I'm already saying given theta star is a minimizer, local minimizer, right? Necessary condition is going this way. These guys, if this exists, assuming this exists, then, or if, of course. Now add the second order sufficient condition theorem. Second order sufficient condition or conditions. If, guys, this is the Hessian, right? Is continuous and positive definite. Definite. And I have this vanishing gradient. Okay. Then this is if, now then theta star is a local minimizer of F or of L, sorry. Minimizer of L. Okay. So therefore, sufficient condition and then the necessary condition are met. We can now say if gradient theta L is 0 and we have a positive definite L, positive definite, we know theta star is a minimizer. But like we just talked about this, it's very difficult to calculate this guy in deep learning. So in summary, actually in deep learning, what we do is this. In deep learning, we just go after this one. We want this guy, the loss functions gradient to vanish. You see, we do what we can do. So we search. So we search theta star from this condition only. From this condition, gradient theta L theta equals 0. And we use again to repeat. We use the gradient descent algorithm. We repeat this. Repeat. So for I1 to M, so maybe let me also say loss uses all samples in the training set, of course, right? So J, let's say I just named it J here, the full thing, 1 over M, I1 to M, right? L, the middle L is inside, you see, for each sample, H theta Xi, Yi, right? Now we repeat the loop gradient. So we calculate the gradient for everybody, for I1 to M grad I, L. You see the loss for each instance, Xi, Yi. Now update the parameters. We update the parameters. And this is the vanilla gradient descent or the basic standard gradient descent, okay? So alpha is, remember, our learning rate. 1 over m, you can just average them, it's fine. And L, or grad I actually. This is the gradient descent until, of course, convergence. That's another, remember, in quotation, update parameters until convergence. You can stop with some iterations, etc. So my question to you now is, what problem do you see with this algorithm? You, of course, from the question, you can guess there is a problem here. What is that? Yes, thanks. That's one thing, exactly. Setting the learning rates is some here important design or hyperparameter selection problem. Actually, before that, I'll give you a hint. Other than that, for all samples M, let's say, I mean, just think of ImageNet. It's 6 million samples.
The gradients may vanish so that it wouldn't update the parameters.
Exactly. I mean, we have to go over all 6 million parameters to be able to calculate the gradient, the overall gradient, right? The sum to update or to even switch to this update parameter thing, right? So now we will have something, we can go to the other extreme, something called this, like the stochastic gradient descent. Mert, we didn't yet talk about that. So we will say, hey, then maybe just update my parameters, right? Just using one single sample. So now theta minus alpha, the grad I, or grad theta L H theta xi yi, right? This could be one idea, and this is the loss for one sample. This is grad I, loss for one sample, and some of you hinted to that. By the way, it's called stochastic, guys. You see, there is nothing like a stochastic process or something, but it is a very noisy gradient update, right? This is a noisy. I mean, you see, it has nothing to do with the real gradient. The real gradient is this guy. You have to really sum over everybody, because that's the definition of our loss. Look at the loss function. Its gradient is here. This guy, this is grad theta big L, let's say. So this should be not J, but we've been using L, right? So this is a noisy gradient update. The update step here is a noisy one, but it introduces some, in a way, stochasticity, meaning while searching, we will see actually while searching through here, going in this high dimensional landscape, it at least gives us some randomness, introduces randomness. That's why it's called stochastic, but it has nothing to do with stochastic producers, just because it introduces some randomness, right? But is this what we do? Is this really what we do in practice? This is, by the way, the single sample loss update, gradient update is called stochastic gradient descent. And in practice, we actually use, like you guys hinted, mini batch, right? In practice, we use a batch, we sample, for instance, that's a parameter, of course, hundreds, I'm just saying 100 samples. So in practice, we use mini batch gradient descent. This is like a compromise between, really compromise between gradient descent and stochastic gradient descent. But typically in practice, when we say SGD, guys, we mean mini batch gradient descent. So there is some misnomer there, but it's actually mini batch stochastic, you can say, gradient descent. But I think in terms of definition, this first stochastic gradient descent was really using a single batch. Here, of course, we have now introduced another parameter, batch size. e.g. typical batch sizes we use like 8, 16, 32, 64. It would be excellent if we were, for example, in imaging, if we can use 128. So a new hyperparameter, batch size, right? This is an important hyperparameter, by the way. It really changes, you see, the gradient fully. L mini batch now, because our loss is really like this guy, right? I want to be L H theta xi yi, and in the vanilla SGD we use, of course, not vanilla SGD uses batch size 1 actually, but not used in practice. Not used. It's very noisy, too much noise then. At least start with 8, right? Something like that. Of course, then you can say, hey, I need some computation power there. So now SGD, you see we use it now. When we say SGD, we mean this mini batch gradient descent. Of course, for now, our iterations are K1 to number of mini batches, which is this one, right? This is, remember, flooring. So this is really number of mini batches. I assume you are used to this symbol, so theta minus alpha grad theta, okay, L, it's L or J, I'm using interchangeably. So now B is another hyperparameter. I should also note that. Batch size, another important hyperparameter you should note. Okay? Hyperparameter you have to fix. Okay? I will show you some pictures of lost landscapes later. By the way, I think maybe we may give a break, but Matt, yes, even if we have computational power, actually still, I mean, increase your batch size. I don't have that much computational power. I've never tested, but probably at some point it may saturate, because this randomness, this noisiness it is introducing is excellent. So it would have been great to compare these two by doing the full gradient, and maybe from there decreasing the batch size, you know, coming from millions to down. But I think all at most what we were able to do were maybe 128. I doubt we tried 256 if it's an image, especially imaging problem, working with images, convolutional neural networks. So good question, but it's still, I believe, better to do a mini batch gradient descent or stochastic gradient descent, because it's really helping us at least a little bit probably to get out of local minima. So here, if I had some loss ISO curves like this, so let's say this is my theta. I mean, just imagine these are of course always in higher dimensions, but our visual display devices are 2D, so that's why we are projecting them to 2D. But you know, we calculate the gradients here, and I'll just try to make this up, but I mean, maybe I am more. So gradient descents maybe going more smoothly. Maybe let's do one more step, right? If I started here, let's say theta star was here, this would be, for instance, I'm just, of course, hypothetically drawing something. This is gradient descent, but supposedly the SGD is more okay, it's difficult. I'll show you some slides. So it's gonna be probably doing things like, maybe I'm here, here, just really making this up, but you guys got the point, I think. Maybe jumps here, hopefully converges there, or it may be really missing it, but you are somewhere converging somewhere here, or stopping, you're lucky to stop somewhere here. Of course, here you see the learning rate may be also, like you guys, one of you responded, if you choose, for instance, a very large learning rate, you may be completely oscillating here, even if it's a SGD or, you know, normal gradient descent. You should not be doing things like this, right? You may be really missing the oscillating around the minima. So, but still, SGD, even if wanders around minima, it may oscillate, but still, hopefully, it's getting you out of many of the local minima there. So there is this thing called an epoch, right? One epoch, probably most of you know, but if you don't, just let me say, one epoch is once you've seen all the samples. This is once you've been through all the samples, right? Samples in your training data. Because you typically, this is epoch is important because how long, so let's say you completed this for a set of or this many number, then that's one epoch, right? And you continue actually with this. So actually you, last time we said this, but you guys also monitor things like that, right? Şuraya bastım herhalde. I think I know why I should not have number of epochs, or sometimes this is one for all the iterations in going through the data, but you may also do this is fine. You may also plot this every some certain number of iterations too. Remember, this is typically what we have to babysit, checking for convergence in the optimization, in your optimization, right? You guys should look at these curves. Maybe if you, last time we were mentioning, if you see things maybe like this, still it's learning, right? It's really, maybe this is, you may be like, hey, if this is really a large number here, you may think, hey, this is really going very slowly. This is a small learning rate. That's one of the first parameters typically we play with. So you may really play with it. And if it's really large, maybe it may actually, if it's really large, you may see things like that, things may be increasing. Then, of course, in this case, you need debugging, debug your implementation. Then if you here you solve this and you decreased your LR, maybe hopefully you see some nice learning rate where you see your loss has fallen to some desired level, and that's nice. Okay, that is a good learning rate, let's say. What else? And also there are learning rate regimes people also fix. I think there are exponential decay ones. There are, I think, these inversely proportional to this number of iterations. If it's time, let's say, you named it as time, L of theta. Now, this is, or let's say L sub theta, because this curve is not a function of theta. This is L sub theta. Here it was function of theta, right? What I'm showing were L theta loss curves here. Lost landscape. It was the lost surface. So, for instance, there are regimes like, okay, it's decreasing, let's say, but you decrease your learning rate. Change your learning rate. maybe it's going like this, you may be doing again, etc. I mean, this is, so here, for instance, decrease LR. You have different regimes. And for instance, again, decrease LR, etc. This is also when you talk about there exists different regimes. This is also some, in a way, hyperparameter, right? Fixing this is a hyper setting for probably. I could say hyper setting. So my here advice from here is always check your loss curves. Check your loss curves. Okay. So now let's give a break. After the break, we will study backpropagation. Okay. Backprop algorithm. And then we'll continue. Probably that should be enough for today, but let's see. Okay, so we talked about SGD and we will talk about momentum approaches too, but after first, I think in this hour, let's first finish work on the backprop, the famous one of the algorithms, right, in probably 70s or 80s that made neural networks learnable or turned it into learnable machines, learning machines. So my question is now, how do we calculate? How do we compute the gradients? Right, because in order to do this SGD, we need this. I mean, you need to really calculate this guy, right? I mean, look at here. You need, in LMB, of course, you need here grad theta L, right? Li, let's say, because it's for one batch, one of the instances, and you sum it up for the samples in the batch. Okay, the gradients, the set of theta, set of parameters, or all parameters of the NM, of the neural network. Okay, and we said it's really actually superscript, right? W1, B1, 2, B2, and if it's n layers, Wn. So, or K, let's say. I said K here, so just keep the same. K, for instance, K equals 3 layer NN, again, just for the sake of visualization. Okay? And it's a fully connected, or ANN, or remember we said this is really FCN, or sometimes don't get confused. Fully convolutional neural networks may be also shortened by FCN. Just be careful there. So sorry, I should do it nicely. I need to do, okay. This is, I call this my input X, which is A0. So maybe get smaller. It's a K equals 3 layer. We will actually do this for a general network, but A1, let's say A2, and this is my A3. So this A3 is actually my Y, becomes 1 by 1 here. Let's say my input A0 is n by 1. This is, let's say, a P by 1 vector, Q by 1 vector. Okay, and these are connections you can think of. There are lots of different notations, of course, here, but important thing here is, for instance, the first layer weights have let's say P by N, because I want P activation vector size in the first layer, right? So I have V1, then it should be equal to P1, P by 1. So for here, I need the second layer network weights to be Q by P, right? To satisfy these size constraints, and the bias is the output size, P2, sorry, is Q by 1. And then the last guy, the W3, this is 1 by Q, and B is 1 by 1. Now I'm arrived at a scalar at this point, and I have my hypothesis. Again, remember, this is the first component. You see, now I already defined the hypothesis, and we will write it openly though. But I mean, I'm going to write this, but let's also first write the loss function. Loss will be between A3, which is my hypothesis actually, and the last activation, right? And Y, this is the ground truth. So let's say, e.g., this is least squares loss, 1 over 2 Y minus A3 squared, right? Now the second component, loss is defined. We've already said this, but the thetas that we are parameterizing against are these guys, right? Just to, again, write it for this specific network. In a forward pass, I would do this. By the way, let's answer this question, backpropagation, because that's what we are studying, and I'm writing now that as a title to my slide, so it's in your slides, right? So backpropagation is the optimization for neural networks, right, to obtain those theta stars. So forward pass means I need to compute my activations, A1, A2, and A3 in this case. But let's make this, now I'm going to go to a general actually network, if this was a K-layer network, and I have my L as now between AK and Y, the loss function between the last layer output and the ground truth. Normally, for this network, given network, right, the what we have is starting by, maybe let's start by A1, where I have the activation F1 could be something we will talk about. I think we've already mentioned what they could be. I can say A0 just to generalize. That's the input, right? B1, A2 is, let's say, an F2. It could be a different activation, though we typically use similar activations. Takes the second activation. I'm actually just going through the network, right? What is happening at each layer. Here, A3 is F3, W3, A2 plus B3, right? This is what happens. By the way, this is typically, we call this affine layer output. For instance, this is my Z3. So maybe let's write this for a generic layer. So actually, AI is Fi, this nonlinear activation. You see uses, I will generalize it by looking at what I just wrote for 3-layer network, uses the weights of that layer, omega I, right, times the previous activation, plus again the bias vectors, parameters of that layer. And also I have also, of course, we have this in parentheses, Zi, which is actually the inside the parentheses, this guy, AI minus 1, this is plus BI. I'm writing these openly because these are my things that I will take my gradients on. And this is actually hypothesis function for each layer in a way, right? This is really hypothesis in a way, if you think of it layer by layer, right? For each layer in an MLP or in ANN, let's say, artificial neural networks or fully connected layer networks, and however you want to call it. So this is, maybe let's use a green color. This is 1. Again, 2 was defined here. Let's make this green. 2 was the loss. 1 is the hypothesis function. Of course, we use the final. I mean, this was 1 also. Now, optimization or equivalently backprop. Let's do. I think it's clear until here for everybody, right? This is a typical fully connected neural network. Hypothesis functions, plus we said, I mean, it's fine actually, you can choose any loss function, you define the loss. Now third step or third component, we do an optimization, and it's gonna be backprop algorithm here. Backprop, that entails or requires us to find these del L, okay, L were here, these are L, right, L, del L by del WI, but pay attention, this is a matrix, so it creates some complications you have to deal with, del L by, and this is a loss function, it's a scalar function, and it's with respect to a vector, which is maybe more manageable. This is equivalent to what we've been saying or calling this gradient, or maybe I think sometimes we called it like this, mainly we called it in this way. Now, forward pass, we know, we said we do this guy. Now, backward pass, as the name implies, backward pass. Now, let's look at this guy, okay? We will, I mean, our derivatives are always based on the chain rule, okay, based on the chain rule. We are after this guy, right? Del L by, let's say, del, with respect to, let's take the derivative with respect to the first guy, first weights matrix. So we would have to, guys, maybe actually I can do a network here. So, something wrong happens. Sure. So, okay. So I can say, let's at this point, you remember we started with A0. The forward pass is calculation. A0 is the input, I mean, as A1. Okay, this was A0. A2, right? We go all the way to and AI, these are vectors, activation functions, okay? And we have an AK, maybe if it's a K layer network, K layers, FCN or ANN number, and I have a loss function. So this forward pass we calculate these. Now I'm going back, right? I need to do del L by del AK with respect to, for instance, these guys. We will name these. These will be my upstream gradients. So we will be now seeing how this is managed. We have to go back because then remember, important thing is taking derivatives, let's say just the weights with respect to these guys, right? So that's the point here. So here this would be WI. Right, plus 1, this is WI, right, in calculating AI. And then the last guy is then WK. Okay, so this is what we are after here, del L by del AK. We will be doing, so let's go and write this one up here. I'm trying to do this backward thing. Del L by del AK, right? And then use the chain rule. Del AK by, I'm going back, right? AK minus 1. And I need to go all the way to del A3 by del A2, del A2 by del A1. and then del A1 by, this is now the derivative I'm after in this case, right? Again, just be careful, this is a matrix derivative. And then the same thing do for also del, for the bias weights, del L by del AK, del AK by del K minus 1. I mean, it's all chain rules, so I'll just go to del A2 by del A1, and the last activation in this case with respect to, you see del A, here we were here. We had this actually del A1 by del omega 1 and B1 was there. Okay, so let's continue del A1 by del B1. So first, this was PY1, this is PY1, just to remember their sizes. Okay, so now I have to calculate, this doesn't look nice, del A1, okay. I have to calculate these different derivatives here, guys. Look, I need these, guys. I need, for instance, these, del AI by del BI, I need, okay, I need a del AI by del AI minus 1, and the of course an important thing is that I need del AI by del WI, right? So I have these activations with respect to previous activation. These are those local gradients. We call them local gradients. And I need also these actually activation with respect to parameter gradients, right? These are important. Again, keep using the chain rule. There will be, for instance, for this guy, just read it off. What is the, just always keep this picture in mind or equation in mind in this box here. For instance, I'm after now del AI by del BI. Just do the math. I need F prime. By the way, that's a pointwise nonlinearity. Okay, so I will have a diagonal matrix with those, each of F primes with respect to each component of the vector on the diagonal. Okay, so that's why this guy will be, this del F del Zi will bring me a diagonal matrix. So this is really, I'm sorry, times. So I will use the output of the actually affine layers before the activation Zi. You see another chain rule, right? Del Zi by del Bi. So this is, like I said, a diagonal matrix by F prime. I mean, with its argument is Zi times here. It's a vector of ones, right? This is vector of ones. Why? Because I need to really have or single out those diagonal elements, right? I'm taking a derivative with respect to here B vector. Okay, so I'm doing actually the first one. Now let's do this del AI by del AI minus 1. That's also here in the first equation in the box. Its answer is there too. So let's just do this guy. It is again del F by del Zi, right? Because I need to first do the chain rule to get rid of the nonlinear function. Now it's del Zi by del AI minus 1. Okay. Again, this time it's diagonal matrix. This is a matrix, diagonal matrix. So diag F prime, sorry, F prime of the I times the WI matrix. I'm just reading these off from the equation, okay? And then the last one, del F by del Zi, and then del Zi by, here guys is the thing, problem, not problem, but I need to vectorize this. Here things get ugly. I warn you, they get ugly. I just vectorize this guy. Now let's see how to take this derivative. Okay? So this is, you can read this off at this graduate level. You can really follow what I'm doing. It may sound a little bit, maybe it may look difficult or complicated, but you are, of course, in a position to go over these. So what we will do for this vectorized gradient is we'll say, hey, I have an identity. We'll use an identity. This is the identity. We will be using vectorized form of multiplication of three matrices is equal to, I can rewrite them as a vector, sorry, the matrix C. C becomes a vector in our case. That's why I said vector. So C transpose of that matrix, Kronecker product with A matrix, and then times the vector B. So this is what we will be used. Vectorized form of B, I mean. And also another recall, we are using this identity. Okay, this identity. This is a side note here. And also recall Kronecker products. This is something you should also know at this level, as a graduate level person in computer engineering. You are supposed to know this already. If not, go ahead and check. So this is BP by Q, okay? You see C becomes a matrix in, remember, Kronecker product. I take, for instance, an element from A matrix multiplied by the B matrix, all of the B matrix. So first A11, so let's do it actually, maybe. Write it here. So it's really like this, A11B. A12B, I think you'll recall this, right? So A1 and B, it will become a huge matrix, right? Then this whole thing, you guys can see AM and B, AM1B. So this C becomes actually, then in the end, it's a R M by P, right? Because we have everybody here, N by Q. It's becoming Kronecker product really enlarges your, just combines the two matrices point by point. That's the idea, if you recall this. This is a recall Kronecker product. Now, the reason I mentioned these on the side are I'm going to use them. I'm rewriting my affine layer output, Zi, as I times the matrix. This is identity matrix. Of course, with the corresponding or necessary sizes in these matrices, you can calculate AI minus 1. You see, this is exactly my ABC here. We will be using these guys and plus a bias. So we can use these to rewrite these guys, use the identity. Now it's really the activation function minus 1 transpose. So that's my C. Use the same, Kronecker product with the identity times. This is what I want. Great. Vectorized weight matrix, because I want to take my derivative with respect to now a vector at least. Zi. And now I can do del Zi. Remember, why am I doing this? I needed del Zi, my activation function before the nonlinearity. I need to derive it, take its derivative with respect to the weight matrix here, a huge matrix, but I vectorize it. Now I can take the derivative by del vec Vi. This is nice. Omega, sorry. Now this is a now vector, so which is nice. I can take a vector derivative, and it's nicely seen here to be exactly this guy. Okay, which is nice in terms of activation and just combined with the Kronecker product with the identity. Now we define also our, we need to define some recursion, not to really calculate everybody all the time. On these guys, we have a recursion here. So you see this loss, the derivative of the loss with respect to the activation. So this will give us an easy way again to calculate our derivatives or backpropagation. This is the backpropagation algorithm, by the way, del L by del AI. You see loss with respect to activation at each layer. This is, remember, we call these upstream gradients. These are called upstream gradients. So we're going back, right, in the backpropagation. Upstream gradients, we need to calculate these guys 1 to k, okay? So we need, really, we start with gk, start with this guy, and it's doable, right? Because loss is calculated at the end. I can do del L by del LK with respect to last layer, which is cool. Start with this. So maybe I should say start with this guy. And from there, calculate. So calculate this, then use that to calculate gk minus 1 all the way to g1. That's the idea, okay? And you can see that's how we are coming gk minus 1. All these guys have to be calculated. So all the way to G0, I guess. Maybe I don't. At the last layer, I may need it or may not. You guys can check because I'm there. I have to be doing del W1 and del B1. Okay, let's keep it as it is. So want a recursive computation. Want a recursive computation here. Let's see. What I can do is I can do gi minus 1 is, I mean, it's already defined to be the loss, derivative of the loss with respect to the del AI minus 1. And this is now, again, come back from the last derivative, right? Del L by del LK. And remember our chain rule. Del LK by del LK minus 1. Dot del AI plus 1 by del AI, and dot del AI by del AI minus 1. That's the definition of my upstream gradient at the point I minus 1. Now this guy can be written as, we've, I think, already seen this. There is a GI here, right? One part is, this guy is GI by definition. Actually, we'll write this to this side, just take the transpose of the first part, and we've already calculated this here. I'll take a transpose of that, and this one will be WI transpose diag F prime. Okay, fine. Okay, so now I have this was F prime ZI, it's fine in parentheses, that's a function of that. Now my target derivatives, remember, are these guys. Target derivatives, right, are loss, derivative of the loss with respect to all WI and L. Actually, I showed them by, it's the same idea, but okay, I showed it like this. WL, L, and L. And I need for all the layers, right? These are my target derivatives. Now let's write them. We found it. Actually, we said, okay, this guy this is one of the target derivatives. It comes through nicely upstream gradients. Remember, we just named them G. They are del L by del LK, and the local gradient, which is del A by del W, for instance. So this is an upstream gradient times, remember, this is really diagonal F prime. Am I? Okay, it's in the GI prime. F I prime, let's say. Okay, maybe let's just keep it without its arguments. Let's keep it in this way. Then I have AI minus 1 transpose chronicle product with I. So I'm bringing this. Remember, we found that local gradient before. Here. Right, we have this one was del ZI by del Vec WI. So this is really the local gradient, which is, I mean, del, I need, of course, del AI by del WI, right? And we vectorized it and come back, of course. So this was in vec form, vec WI form, okay? So that's why things may look a little bit not nice, I admit. But I mean, that's how life is. So upstream gradient times the local gradients, right, is what we need, of course. So now I can just summarize the backpropagation algorithm, guys. We can just summarize the backprop. I mean, I will add the derivative with respect to B vector 2, the bias vector, summarize. So first, of course, we do a forward pass where we calculate these activation functions, Fi, Wi, Ai minus 1 plus Bi. We do these guys. And remember, I mean, this was really my Zi. Now, backprop algorithm. So this do a forward pass, okay? Maybe actually let's write it in a, or let's start here. Okay, backprop. Okay, I started it on a new page, so let's see. Backpropagation algorithm. This is the whole summary. Parameters we search for are theta W1, V1. Okay, this is up superscript all the way to a K layer, and this is for a K layer neural network, right? K layer, and then now, of course, fully connected. I mean, you know the hypothesis here. So, okay, just to be complete, you need to do a forward pass first, of course, to compute. You need to compute A1, A2, let's say maybe all the way to AK, all layer activations, and your loss from the last layer. It could be ZK, but that's a small technicality. And also, at this point, you can local gradients, which is nice, guys. Because upstream gradients you cannot compute, because you see loss is computed last. It can be, I mean, without AK I can't, but as I go forward I can compute local gradients, which are these del AI by del AI minus 1. Also compute local gradients. Okay, so I can have del AI by del AI minus 1, del AI by del BI, and del AI by del WI. So these guys could also be computed and stored. You compute loss, compute local gradients. Now do a backward pass. Backward pass now entails computing the upstream gradients, okay? Compute the upstream gradients. Now, GK, remember, compute recursively. Compute. So you start with GK, of course. GK to G1. Remember, upstream gradients are these GK, actually, del L by del AK. Okay? And from here, remember, we get GK minus 1. From here, we get GK minus 2, etc. Just remember, from today, you need to calculate local gradients. You need to calculate upstream gradients. And how did we do them? We calculated actually the formula GI is really this W, the weight matrix, transpose times the diagonal matrix with the F prime, the nonlinearity on its diagonals of ZI, let's say, times GI minus 1. Okay? This is it. Now, I need, so this is computation of recursively my upstream gradients. Third is compute now the gradients of the loss with respect to the parameters. That's the final step. Compute the gradients of the loss function. Loss function with respect to theta. Here it is. So that is this, right? Wi. For instance, this is n by p. Del L by, remember, we were saying this is really del vec Wi. And we've actually just seen how to do this. Gi times, again, the diagonal f prime. And at that layer, and the previous activation transposed with a chronicle product identity matrix. So this becomes here at this point, my point was 1 by NP. Okay? So what I'm trying to say here is actually then this guy is could be calculated as 1 by NP. You convert it back to a matrix, of course. You need to use it right in your updates. You can still update as a vector, but you need to at some point convert back to a matrix. Okay. So now this is maybe more straightforward because this is with respect to a vector itself, del L by del BI, right? Again, GI. This time it has diag F prime without the A. It's I. I wrote P by P here. Now this becomes already a vector, which is fine. Now the fourth step is update the parameters. Now I have everything I need to update the parameters, okay, in my backprop. This is something you guys will be implementing in Python without using any built-in function. So that's why, and this is already assigned in your homework. So we should update WI with WI at the previous iteration. So probably we should say iteration step T, maybe, right? T minus 1 minus alpha. I'm just showing my stochastic, vanilla stochastic gradient descent, but you guys get the point. You already know you can do different things here. Loss at the previous time point, right? T minus 1, say, do the same for BI at time T, BI at time T minus 1 minus alpha gradient BI, loss at the previous time point. So this is done for each layer I, okay? So all I's parameters, let's say, I's parameters. So that's for I1 to K layers. For a K layer, for a K layer, and neural network. Okay? So this completes the backpropagation algorithm, actually written really in detail. Here is a note, actually, guys. Maybe I can note it in this page. So let's maybe save. Sorry, myself. Why am I going to this now? All of a sudden. Okay, I switched to another note. Mistake. Okay, so my goal was to open some space here. Convert back to a matrix. Let's write it here. I will say note here. Note. Just to have it in the same page is good, I think. Sorry, what's happening here? Forward pass uses, this is what I'm trying to say in this note. Forward pass uses, okay, let's say uses here, multiply by, so it's really uses multiply by W, the weight vector, right? Why? Because, I mean, here is the forward pass, of course, it's quite simple. Here is the forward pass, here is the multiply by W, right? This is forward pass. Now, backward pass uses, you can see, a multiply by W transpose here, this guy. So it's trying to say that forward pass uses that, backward pass uses. Just be careful in that when coding this, that's why. Multiply by, okay, this is something you should note. Note this in your implementation. Now you have everything actually you need to be able to code, implement backpropagation algorithm. Any questions until this point? I mean, I used some upstream gradients, local gradients, right? In order to, what were the upstream gradients? They are the del loss, derivative of loss with respect to activation layer, for instance, from the previous layer, let's say, it comes and it gets multiplied by the local gradient, right? Upstream gradient gets multiplied by local gradient. These things can be also traced back on things called computation graphs. We can take a look at them next time. I think some courses have slides on those. Nice computation graphs. Maybe Stanford CS231N has, I think, some of those where you see the multiplication of this upstream gradient coming right in the backward pass and getting multiplied by local gradients in order to obtain this final gradients with respect to the parameter theta. Okay. Here the upstream gradients. And local gradient, right? The same for the B vector. Okay. All right. So I think if you are fine with it, still we continue with studying the optimization component of our ML algorithm, the third component. Now we will exactly actually work on these variants of, there are many variants, of course, we can't study of all of them, but for instance, study some of them. Gradient descent with momentum, for instance. Idea is here smoothing out your gradients, right? And like you guys said, maybe it speeds up my gradient descent. Also, it overcomes my oscillations because my stochastic gradient descent is too noisy. Of course, this is always SGD with momentum. So idea, smooth out. How do we do this? Actually, we use gradients from the previous iterations, right? Smooth out your gradients to speed up and to improve your gradient descent. So we will then, like I said, try to introduce something. The reason its name is momentum is it's like we are introducing some inertia, some resistance towards updating the gradient fully. So we add, try to average, start averaging or taking a weighted average of previous gradient plus the new gradient. That's the idea here. Okay. So at iteration T, let's say, compute this guy. we will have, okay, we will call these, okay, maybe I should say these guys, we will call d omega, this guy we've been calling, right, before grad sub BL, dB, these are vectors, of course. We compute these on the current mini batch, or in the current mini batch, remember, that's the idea. We add momentum now. Momentum, you know, bring the information or the mass from before. You initialize these guys, remember, by dW or VW. Maybe I could have kept them as dV and dW, and but let's keep it as they are. Okay. So actually, yes, this is something, because this is the this is the accumulated gradient. So this is fine. dVW and dVB is 0. Now we, at each time point, we are calculating. So we have new parameters now. What I'm doing is, guys, okay, this was 0, but it's going to get accumulated. I'm accumulating some weighted average of gradient term where you see I have, okay, let's not write the true gradients, right? Current gradients, the dW, this is current gradient, and previous gradient dW. So let me write also the V version, and the VB plus 1 minus beta 1 dB. So these are current gradients at time t, let's say. These two are my current gradients, right? Current gradients at t, dW dB. By the way, beta is a new hyperparameter. I said beta 1, but okay, beta 1, a new hyperparameter, as you can see, right? Now, this is previous gradients. Okay, so these are, this one and this one are coming from the previous step, weighted averaged, of course, previous gradients. Okay, now I calculated the current weighted average gradient. Now I can update. This is SGD with momentum. Now update the parameters. Okay. So W is W minus alpha times dVW. You see, I bring this and use it in my, of course, it's at time t. I'll add the iteration numbers. It's or index t, right? I should just update whatever I had there. T, this should be t minus 1, right? I need to update those. So this is something called momentum update, GD with momentum, this algorithm. Is this idea clear? It's also, it can be interpreted as a, actually, you see, the way we write it here, it can be interpreted as also an exponential smoothing of your gradients, because I take my current gradient and I take an accumulated gradient, you see, dVW beta times dVW, but of course beta and 1 minus beta do a convex combination there, and they weight it. So for instance, beta, I think typical parameter, let's say, is 0.9, just of course, I can't say typical for your problem. By the way, I should also note a bias correction term here added. A bias correction is added. Why? Because typically in the beginning, I may have, if beta 1 is 0.9, I may not be using my initial gradients a lot, right? And you see, I initialized my dVs as 0, so I may not be really getting a lot of updates in my gradients. So That's why we add a bias correction here, okay? Some time to think about these. The bias correction, probably you guys also seen this, and the reason is, for instance, let's say I'm at the first iteration step. Now, something like this is added actually. What is, let me first write the bias correction. It is in this way. It is divide by 1 minus beta 1 term, this dvt's of both. Okay? Why, for instance, let's say t is 1, 1 over 1 minus 0.9. You see, this is a large number, very large. Now, it's trying to actually help me add more momentum initially, but as t grows, t is 10, let's say, and I think, oh, it was to the power. Sorry, this is like this. Guys, beta to the, no, it's in this way. Please check this. I'm trying to go all the way to here. This should be it. Okay. So this is called a bias term. This 1 over 1 minus beta times t, beta power t to the power t. So I was going to say, okay, this is 1, which is fine. But if it's now for later, as the number of iterations grow, my bias term now becomes 1 over 1 minus 0.9 to the 10th. This is really small, right, in the denominator. So this is really 1. So after it really accumulates itself, that bias term will not have much effect at the later iterations. This is just a bias correction for the first few iterations, added in a way to affect initial iterations. Okay, that's something you will see when you deal with this. That's why. And after a few iterations, actually, it won't affect. After a few iterations, bias term has no effect, as you can see here. These are heuristics, guys. I mean, nothing, none of these are really, you see, coming from like mathematical, rigorous mathematics. This is engineering currently, what I just noted here, okay? Okay, so I'll actually now, is this clear? This was momentum. I'll talk about RMS probe and Adam optimizer, which are really variants again of this momentum idea. Any questions? Are you familiar with these, or is anybody seeing these for the first time, or has anybody seen these, like in these details? Nobody has seen them before. Okay. All right. So let's go to RMS probe, gradient descent. Now, this one, this was adding somehow a mean, right? An average, exponentially smoothed average. Now we'll also add the squared gradients. We'll also collect in this time in our momentum the squared, the gradient squared, and bring it as a normalizing term with like actually square rooting it. So it will be like actually standard, using standard deviation of the gradient. So at iteration, T, we want to compute again and save, right? Record these, save dw, db. Okay, these are what we want, but we will be computing these. Compute these momentum-like terms, SDW squared. Like I said, now another this is the variable itself actually. Another averaging here, SDW plus 1 minus beta 2 dW, the current gradient. So this is, you see, the previous averaged square gradient and the current gradient. Same for the bias term. Current gradients, okay? These guys are current gradients, by the way. Now, update rules are RMS probe update rules are these guys. I have, for instance, W minus alpha, dW, vector or matrix, whatever form you convert it to. If you are back, which is fine. dW over, here what is nice is now you see these were square gradients collected, exponentially smoothed or averaged out. Now SDW, of course, it's in the denominator, so it's always good to add an epsilon. And now do the same for B, the bias term. Okay, and these are really like normalizing my gradient, you see, by standard deviation of the gradient. Okay, this is called RMS probe. Now there is something called Adam optimizer. If you are fine with this, this is Adam optimizer. This is a combination of momentum and RMS probe. So both uses mean momentum and the squared momentum. Okay, it's a combination of momentum and RMS probe. Right? So updates. Now I'm not writing the calculation of these other terms. We've already written them. The update is at iteration t. Okay. Now W takes W minus alpha. You see now dW bias corrected, by the way. dVW, sorry, if dW we call the original gradient, so it's dVW bias corrected over, guys, the SDW. Again, these are also bias corrected because you're doing this accumulation, right? You need to use bias, not use bias corrected versions, of course, bias corrected versions, which are, for instance, the VW bias corrected is the over 1 minus beta, for instance, 1t to the power t, okay? And now do the same for B minus alpha, dV, B corrected over SdB corrected plus an epsilon. Okay. So now initialize, you have to, I didn't write this, but I mean, I need to initialize some things here. Initialize, these are all zero, right? Because I'm collecting them, accumulating them. The VB is zero, the SW is zero, the SB is zero. At each iteration, these guys should be set to T. And now you see I can compute dW, which is this full thing. dW is my, maybe I can show it. I mean, the final dW, of course, is this here, and then dB is this. But at each iteration, we also, of course, compute the current gradient. dW, dB, current gradients with the current mini batch. And then with the current gradients, these are current gradients. We also, of course, compute these guys. These momentum, I mean, accumulations, VW, DVB, and DSW, DSB. Okay? I mean, if you do all these calculations, computations, we are fine. And we can compute the ADAM and RMS probe or momentum. Okay? I think I wanted to also talk about how to initial, there are rate initializations and vanishing exploding gradients problems. Let me see. Or we can look at these optimization stuff in, okay, actually, let's do this. Just a sec. I'm not sure. Any questions until here? For instance, last year we were checking NeurIPS. We won't be doing these actually, but anyways, I will talk about vanishing gradients, etc. next time. But anyway, so let's first talk about these now. This was other belief optimizer. We actually even ran this, like your question, what to use when. Hey, this sounds nice. This was actually doing updates on the ADAM optimizer. Now you guys, for instance, you see this is a NeurIPS paper. Now you guys are in a position to be able to read this paper because you know what SGD is, you know what ADAM optimizer is, you know the algorithm. For instance, on this side, left side, this is algorithm 1, is the ADAM optimizer. We just studied this. You see, calculate the gradients at time t iteration, put it into your GT, calculate these mean momentum, right? In a way, weighted average mean momentum, MT, we were calling them like DVW, DVB. Now this one is the squared, you see, momentum, the gradient squared, and that is also accumulated in VT term. Now you see bias correction is applied as we just seen here, right? Divide your accumulated momentum terms by 1 over 1 minus beta to the power t. Beta 1 and beta 2 are again new hyperparameters. You see both the mean momentum and the squared momentum are both bias corrected. Now the update step is actually, you see, theta is updated by theta minus alpha times this mean momentum at time t over, you see the in the square root of squared momentum gradient plus some epsilon. Actually, epsilon could come outside too. So other belief optimizer, guys, these guys actually proposed it, for instance. Now you see what changed is, here is their idea was, instead of collecting squared gradients, let's look at collect centered squared gradients. So I'm collecting already a mean momentum instead, right? In a way, an accumulated momentum, first order. That is, you see, subtracted from the gradient, current gradient, and square it. Collect this guy, you see, and do your again bias correction. You see now you are updating the parameters by this time by dividing by this variance like or standard deviation. This time it's really standard deviation. This was their idea actually. That's the highlight of this paper. There are many things probably out there they worked on, but you guys can check. Probably, you know, you have to of course compare to when you propose something like this. Actually, at a belief, let's say, right, they compare to top 1 accuracy of ResNet on ImageNet, SGD compared to ADA bound. Okay, there are others. ADAM, you guys know, Probably they compare to RMS probe somewhere, or you see there are tons of other variants, Yogi, for instance, and they are supposed to get the highest number. And actually, I think we tried this with your one of your TAs, Gülçin, and for instance, it didn't work better in our case. In the problem, we were trying also a toy problem, I think, and the code must be available. They have a GitHub repo. You can always, of course, be curious and try to check these different optimizers too, because this is, you see, once you change, for instance, from Adam to Adam leaf, your ML algorithm becomes a completely new ML algorithm, actually. Like I've been telling you from the first week, you play with those 3 components, you get, for all those variants, you get tons of different ML algorithms. So guys, also here are some nice slides. These are from François Fleuret at EPFL. This is the course you guys can see if you want. So I like these visualizations, that's why I wanted to get them. But maybe actually I should open it here because then we can really talk about by drawing things on top of it. Okay, so that's my goal actually, probably. So let's open that here and share it on my screen and on my tablet screen. Okay, there is some slowness in my monitor now, so I opened that PDF from this another class notes. I like the visualizations here. So guys, it says, okay, I mean, or it shows here, let's say, what we call a lost landscape. So that means, I mean, these are theta, right? These are, okay, maybe I should open it somewhere else, by the way. Let's open it in PDF Expert. Ah, okay. So these are, for instance, okay, so just a sec. Theta 1, for instance, theta 2, of course, right? I mean, again, we can only visualize this much. So you see, we were looking at these 2D ISO contours there. So gradient descent makes a strong assumption about local curvature. It assumes I have enough gradients, right? When I start somewhere, you know, I'm trying to really move towards, I mean, if let's say the projection is here, I'm trying to really move, hopefully. I mean, these should be, of course, in the gradient direction, but that's the goal, right? That's our goal. And that's, of course, I'm showing here a convex function, but for a non-convex function, we will have many, many of these guys. So here, it makes an assumption, it says about isotropy. That means actually in both directions or in all directions, we have similar gradient sizes, and we can really look at them through, remember, the eigenvalues of the Hessian. Eigenvalues of its eigenvalues, guys, the Hessian eigenvalues. I can check them, right? For instance, and I can look at, typically for well conditioning, you want to look at isotropic means, or well conditioned means small eigenvalue and large eigenvalue are similar. Can you follow me, by the way? My computer is freezing from time to time. There is a lag, actually. So, for instance, well-conditioned Hessian, isotropic. So, you see my steps in both directions. Actually, here it would be really nice. I mean, there is a show already. You see, there are steps here. Nicely, you converge towards the minima. I mean, this was already a nice convex function. So this is the step size, guys. Okay, well, it was 10 to the minus 2. So for instance, now this is, you see, this was isotropic, right? A nice ball, more, you can think of the isocontour spherical or circular. Now think of this case, my loss landscape, loss function change. Now this is more like you can think of this as a ship. Think of a ship, guys. It's like a ball in this case, like this. It's like this ball. This time, I mean, try to visualize it from above, right? Exactly. I mean, what we are showing here. Now you see it's very steep in one of the directions. So that's lambda max, lambda 2. I mean, it's two-dimensional here, but for high dimensions, it's lambda max. This is much larger than lambda 2, or here lambda 2 is much larger than lambda 1, and this is a problem. You see, now you are really, because this direction is really very shallow. This is a steep direction. This is a very shallow direction. You see, I'm not really progressing in this shallow dimension. This is a problem. Okay. So let's see what happened. I think here the step size changed. You try to change the step size to see whether it's going to remedy your problem. No. You see, you increase the step size to 2 times 10 minus 2. Okay, not really doing great. So let's also see, now you're increasing to 4 times. I mean, it's at least now you see, because you see, once you increase the step size in this the steep dimension, oh, you have done a big jump now on this direction. But still, on this other shallow dimension, you are going very, very slowly. That's the problem. Okay. So now let's see, for instance, if I do 5 times learning rates, I'm doing these oscillations, okay, in this case. So I want to see if I'm really making, yeah, and you made it even bigger, and you actually now, you see, it was 5 times 10 to the minus, you made it a little bit larger, 5.3 times to the minus. So you see, now you are missing, if this was your local minima, you are going to miss really the minima, you will oscillate, and you are really even diverging from the minima. This may be things that you are observing sometimes, your actually loss does not converge. I told you, you should always monitor your loss curves, right? These guys, number of iterations or epochs, L theta, right? Maybe not converging, or it may even start diverging up. I mean, this is, of course, just a guess currently. So remember now, what I've shown you also, some optimization methods leverage higher order moments, meaning these momentum terms, first order momentum, second order, we added squared one, right? Of course, resulting computational overhead, is it worth it? Sometimes you may notice actually it's not. There were papers in NeurIPS in the past years saying SGD is all you need, for instance, things like that. So really, there is no single actually remedy to this, but okay, here momentum and moment estimation is mentioned. We've already been through this. This is our mini batch stochastic gradient descent with batch size B. First improvement is use of momentum. We already did that. This is, you see, the momentum term, gradient, current gradient, and the previous gradient, averaged out gradient. Now my update is with that, done with that. And of course, gamma equals 0. Here, gamma was I called it beta in our notes, but here it's gamma. Gamma is 0. This is the vanilla stochastic gradient descent. And if gamma is 0, let's say it's trying to say it can go through local barriers. I mean, that's, I think, hypothesis these people are saying. it accelerates the gradient if the gradient does not change much. Okay, this is shown through the equation, which is correct, because you see now we're using u, right? And u is gamma u plus eta g, let's say. And from here, you can solve for u in terms of g, even if g is small, very small. Here, this gamma, if it's between 0 and 1, this term can be large. You know, it can give a push to the gradients. So, okay, that's a plus, for instance. It may dampen oscillations. Let's just check, I think, some of the results here. Okay, this is gamma 0. It's still the stochastic gradient descent with no momentum, with this step size or learning rate 5, 10 to the minus 2. Now, let's see what happens to this trajectory when we add momentum. Okay, momentum is added with momentum parameter 0.5. You see, you know, we were not, this is, remember, that ship-like lost landscape. Shallow in one dimension, steep in the other. Ship's two sides, right? It's very steep, but from the front and back end of the ship try to come down. It's a very shallow, less steep, much less steep slope. Now you see, actually with momentum, for instance, for this simple example, of course, it's a 2D lost landscape. It was able to, but I mean, synthetically it's shown it can help to converge, help the stochastic gradient to descend to converge to the local minima. Okay. Now this is another one. I'm going fast because we've been through this. Now it says Adam uses moving averages of each coordinate or each gradient and its square. So this is the Adam. We've been through this. Now we have the squared gradients. I've even shown you further things than Adam, like Ada belief, which is really, for instance, minimizing or adding, sorry, a center gradients. Okay. Okay, so this is something we've seen already, and with Adam, you can compare, okay, again, a smooth, nice descent for this toy case. There are many incarnations, Nesterov, you use vector additions of these gradients and stuff like that. You can use torch optimizer. This is, I think, something you can go over with if needed or ask your TAs, or you as a grad student can follow up on. PyTorch, torch optimizer. Of course, I think in the beginning of homework, you are not allowed to use these. Later in the course, you are allowed to use things like optim.adam and things like that. At this point, any questions? We've covered actually most of the optimization stuff that I wanted to cover. We'll continue next time with vanishing gradient problem, maybe better normalization, dropout, and things like that. And then we move to convolutional neural networks. So those should be next week. Okay?